Alright, so let's look at the same function that we did in our last video, except this time we're not going to use our calculators, we're going to use some calculus. So if you watched my previous video, we used our graphing calculators to find these extrema points, the max and the min values right here. In other words, we're trying to find the point that's sort of at the top of this mountain and the point at the bottom of this valley, right? And these are what we call relative or local max, so it's higher than all the points that are immediately around it. This is a local minimum or a relative minimum because it is lower than all the points directly around it. It's not the lowest possible value of the function. We can go lower down here. Similarly, this one's not the highest possible value. There's one up here and of course up here that's actually higher, but if we're talking just in the neighborhood, these are important points. So how do we find them using some actual calc? Well, let's get into this. Here we go. So extreme values. Here we go. All right, let's take the derivative of this thing. We're going to use the power rule. And let's see, we get the power rule says, all right, take this 3, multiply it by the number in front. So we get -3, rewrite the x, and reduce the exponent by 1. All right, I have a power video derivative rule. If you want to check those out, go for it. There's also quotient rule, product rule, and all sorts of cool stuff. So check those out if you kind of forget your rules. But 2 times 4 is 8. That's plus 8x, and then just bring that power down by 1. Constants disappear. And of course, we don't actually need to write this power of 1. So there's our derivative. All right, it's denoted by y prime. If we started with f of x, it would be f prime of x. So let's set up a we need to kind of like solve this thing for 0, or yeah, let me start that over. We need to solve this thing by setting it equal to 0. So we just simply take this and we want to figure out where our derivative is 0. Our derivative is going to be 0 anytime that our graph sort of flattens out. And we'll talk a little bit more about tangent lines later, but derivatives basically find the sort of the instantaneous rate of change of a graph at any given point. So in other words, the derivative here is uphill. It's an uphill slope. The derivative over here is downhill. It's the slope of this graph at that instant. But here, the slope of the graph, if I can draw it well, that's not bad, is perfectly horizontal. So our slope is 0. Right? So if we were to draw a tangent line in here, a line that only touches once, it's perfectly horizontal at those 2 points. Alright, we'll find out that sometimes those values won't be minimums, but for our purposes right now, you can clearly see this graph certainly does yield these values where we do have a max and a min. In order to get those x values, though, we need to solve and set our derivative equal to 0. So set your derivative equal to 0 and solve. When we solve this thing, I'm going to bring out a basically our greatest common factor. I like to put out, if there's a negative out in front, I like to take that out of both. So if I take a -3x out of both of these, that's not exactly true because 3 doesn't go into 8. I screwed that up. But I'll take a -x out of both of them. So if I take a -x out of both of these, that leaves me with a 3x and a -8. I'm just kind of factoring out a common factor. Alright, in this case I take the negative out as well. You don't have to take the negative out if you don't want to. You could have easily just taken a positive x out of both of these. So you just kind of ask yourself, what do they both have in common? Alright, they don't have any numbers in common. These are numbers that are relatively prime to each other, but they certainly do have x's in both terms. So I just take an x out. Alright, cool. So now we have what we, of course, I've looked at before, where we say, okay, if we have this thing times this thing equal to 0, that means either this is 0 or this is 0 or both. So we just kind of branch out, use our 0 product property, and solve both equations. So x is 0 and 3x equals 8. X is 8/3. So these are the x values at our potential extrema, and we just need to test it. So let's put it on our number line. So we have 0 right here and 8/3 right here. Alright, so I take these two values and we just want to test them. So I put them on my number line, and I'm going to look at my function up here and my derivative down here. I'll use a different color for my derivative test. Let's use just pink. Alright, what I'm doing here is I'm trying to pick a value that is to the left of 0. And let's make it easy. Let's choose -1. So -1, of course, is to the left of 0 on a number line. What I want to do is test that value in my derivative. Alright, so let's take it back up here. Alright, we see that our derivative is right here. This is our derivative. Let's test -1 in there. So -3 times -1 squared plus 8 times -1. So that gives me, let me make a little bit more room here. That gives me -3 times +1 minus 8. That gives me -11. So this is negative. I don't really care that it's 11. I just care that it's negative. So to the left of 0, anything to the left of 0 is a negative number. That gives me a negative derivative. Alright, my function then would be decreasing. When your derivative is negative, your function goes downhill. Let's test a number that's in between 0 and 8/3. 8/3 is about 2.6. So let's pick number 1. Number 1 is certainly in between 0 and 2 2/3. So if I put 1 in here, let me rewrite my derivative here, -3x squared plus 8x. If I evaluate my derivative for 1, I get -3 times 1 squared plus 8 times 1. So it's -3 plus 8, which is +5. I don't care that it's 5, I just care what sign it is. It's positive, which means my function is going to be going uphill. Okay, let's test a number over here. So something greater than 8/3. How about 3? So if I go back here and I test now in my derivative, I test +3. So f prime of 3. I just want to see what I get. I get -3 times 9 plus 24. -27 plus 24. That's -3. So anything to the right of 8/3 yields a negative derivative. When derivatives are negative, the function goes downhill. Alright, so anytime you go from a downhill to an uphill function, you can see a downhill, anything to the left of 0 is a downhill function because my derivative is negative, so my function goes downhill. Remember, the derivative tells you the slope of your graph. Over here, from 0 to 8/3, my function goes uphill. So from 0 to 8/3, my function goes uphill. And that means that my derivative is positive. And then it switches and goes downhill from 8/3 to infinity. So it goes negative, positive, negative. Anytime that it goes from negative to positive, we have a minimum value. Anytime that we go from positive to negative, we have a maximum value. And, oops, I wrote that wrong. So this is our minimum, and this is our maximum. If we go from downhill to uphill, it's a minimum. When we go from uphill to downhill, it's a maximum. And there you go. So if you wanted to figure out 0, -3, we did it in the last video, and the maximum value is 8/3, whatever it is, 6.4 something, 6.48, I think it was. And to get those actual y values, you would just plug it back into the original. So there you go. Using derivatives, the first derivative specifically, to find Extrema. All right, in a future video, we're going to look at how these derivatives relate to concavity, and then from there we'll get into inflection points, and we'll kind of wrap it all together with a discussion of critical points and sketching graphs, basically without a calculator, getting a really good idea of what they look like without calculators. So thanks for watching, and look forward to my next video.